Lesson 13. Faraday's Law. Section 13.4. Fleming's right-hand rule. Suppose that a conductor of L meters is placed parallel to the y-axis, and a uniform magnetic field of negative BAX Teslas is applied. And the conductor moves upward with a velocity of u. Then an electromotive force V is induced, with its polarity positive in the direction indicated by the arrow. The magnitude of induced voltage is BLU volts. Fleming's right-hand rule is a visual mnemonic for remembering this relationship between U, B, and V. The thumb points in the direction of U, the forefinger in the direction of B, and the middle finger indicates the polarity of V. Exercise 13.4.1. Pause the video, and answer the problem. Find the electromotive force V. The answer to exercise 13.4.1. Pause the video, and check the answer. Exercise 13.4.2. Pause the video, and answer the problem. Find the induced voltage V. The answer to exercise 13.4.2. Pause the video, and check the answer. Exercise 13.4.3. This is your homework. Pause the video, and answer the problem. Find the induced voltage V. Section 13.5. Relationship between Faraday's law and Fleming's right-hand rule. A conductor of length L meters is placed parallel to the x-axis. The conductor is moving in the direction of the z-axis at a speed of u meters per second. A magnetic field of B teslas, parallel to the y-axis, is applied to the conductor. The magnetic force on a charge q inside the conductor is given by this equation. The motional electric field intensity E, expressed by this equation, is induced inside the conductor. If there is a current path, a current I will be driven by the electric field E. This is an expression of Fleming's right-hand rule. Then the EMF V is obtained by performing the line integral of E along the conductor. The polarity of V is indicated by the arrow. E is replaced by the cross product of U and B. Then we can apply this formula for the cross product and dot product. The EMF V is expressed by this equation. This is another representation of Fleming's right-hand rule. Let's explore the meaning of this term and its relationship with Faraday's law. Let's suppose a rectangular conductor and its EMF V as shown in this figure. Cp denotes the closed path of the rectangular conductor. Then, V is given by the line integral of BU/dL along the path Cp. The cross product of U and dL is the area vector shown in this figure. The orange area represents the differential area swept by the differential displacement dl in a unit of time. S denotes the surface bounded by the path Cp. This differential area corresponds to a differential change in S. Thus, BU/dL is the differential change of flux which crosses S. Therefore, the line integral of d delta phi over delta t along Cp represents the change of flux linkage delta phi over delta t due to the rotation of S. This represents Faraday's law. Faraday's law is expressed by this equation. Let's explore what this equation means in more detail. There can be two time-varying factors in this setting. One is the magnetic flux density B, which changes over time. The other is the surface S, which, for example, rotates over time. The product rule of differentiation yields these two terms. This is the term for a time-varying B. The second term is the one for a time-varying S. And the second term can be replaced by this equation, which expresses Fleming's right-hand rule. Exercise 13.5.1. Pause the video, and answer the problem. Find the induced EMF V. The answer to exercise 13.5.1. Pause the video, and check the answer. Exercise 13.5.2. This is your homework. Pause the video, and answer the problem. This is a brief summary. In this lesson, we learned about Faraday's law. The author of this material is Takeshi Furuhashi, Professor Emeritus, Nagoya University. If you have any questions, send emails to this address.